Welcome! In this video, we will discuss the infinite spherical well. Now, this case is going to be actually very similar to what we have seen previously in the cases for the infinite square and infinite cubical well. The main difference here is going to be that now, of course, the potential is spherical. It's going to be spherically symmetric. So the potential will be defined mathematically as we have right here. So the potential is 0 if we are in a region within a certain radius A, and it's going to be infinite outside of it. So if we want to sketch it quickly, I'm going to sketch it off of the origin, mainly because that way we can see it better. So if the origin is here, let's just draw it somewhere over here. So this would be perhaps our region of radius A, right? So if this is some sort of radius A, then inside of this sphere, the potential is 0, outside it is infinite, so no wave function can exist there. So it is the same concept as for the infinite square and cubical well, but now spherically symmetric. So the procedure will be the same. Okay, so do not get confused by some of the crazy things that you will see soon. The procedure is the same, right? So we will solve the Schrödinger equation, right? So we solve the Schrödinger equation, and then we get some sort of solution. Then we apply boundary conditions. And then we basically have our solution ready. So that's the main idea. Of course, it's not going to be all that easy. Why? Because now we are in spherical coordinates. So that means that the Schrödinger equation will be, it will be divided into two parts, an angular and a radial part. The angular we have already discussed. If you don't know how you solve the angular equation, or at least what the results are, right? If you do not know what the spherical harmonics are, then you probably need to go back in my playlist and watch that part because it is quite important. We are now focusing on the radial part first, but of course the complete solution is both of them. So to find the radial part, what we did previously when we discussed the radial part in the spherical situation, is that we used a change of variable, u, which is simply r times the big R, the function r, that we found from the separation of variables, right? R is everything that depends on the radius, or the distance r, sorry, not necessarily the radius, the distance r. And this y are the spherical harmonics that depend on theta and phi, right? Our angles. So when we do that, we arrive at this equation right there. So that is basically our Schrödinger equation that we need to solve. I mean, it does come from the Schrödinger equation. So it literally comes from it. So that is what we need to solve. Now, of course, as you can see, this depends on what the exact values of L are. So we will solve it very soon for the general case L. Let's first start with the easy case L equals 0, which of course implies that M is also 0. And we will just work from there just to get acquainted with this case. So let's solve this case. So when we do that, we get that d squared u, dr squared, is going to be minus k squared u. And this, you may notice, is exactly the same equation that we had for the infinite square well. So the solutions to this are that u of r is a times the sine of kr instead of x, of course, and then we have plus b cosine of kr. Okay, so those are the two solutions that we get, and in case you don't remember where that came from, I have that on my playlist in the channel, and I will just give you a quick hint in case you don't know. So what I like to do here to find the solution is just write everything on one side, so d squared u dr squared plus k squared u, and I write this as minus I squared. So minus I squared, which is of course minus 1, so I didn't actually change anything. Then we factor out a u, we just write it outside, u equal to 0, and then we rewrite this as the sum of the squares, or the product of, so we do d dr minus I, or rather plus ik, I like it like this, even though it's the same, d dr minus ik u equal to 0, right? So if for this to be 0, either this times u is 0 or this times u is 0, and each one of them is going to give you one answer, which will be in the exponential form, and then you can just convert via the Euler formula into sine and cosine. All of that I have done many times in the past in the playlists. I will put the relevant links in the description in case you are unsure. Okay, so once we have these solutions, we have to keep in mind that these are the solutions for u, but the function that is actually relevant is r. Right? That is the function that we want, because that's the one that actually appears in the Schrödinger equation. U is simply this substitution that we use, so we have to undo it. So if u is equal to r times r, that means that r is u over r. So that means that r is going to be a sine of kr over r plus b cosine of kr over r. So that is what we get. Now the question is, well, what are the boundary conditions here? So the boundary conditions, that's the next step as usual. We of course want that our big R, so R evaluated at A, which is the boundary, has to be equal to 0. That's one of our conditions. And another one is that, of course, all of our wave function has to be normalizable. So that means that nothing should blow up. So let's make sure that nothing is blowing up before we do this. So before we go into this part, let's see this first expression. Right? Because they are both divided by r, and r can be 0, right? R could very well be 0 in our domain. So we need to make sure that nothing is wrong. So what is the limit of the sine of kr over r as r goes to 0? Well, sine goes to 0 and r goes to 0. So this is something of the form 0 over 0. So we can use L'Hopital's rule. So by using L'Hopital here, so L'Hopital, we get the derivative of sine, which is k times cosine of k over r, divided by 1, and we still want to take the limit of this. So limit as r goes to 0. But now as r goes to 0, this thing simply is going to go to k, because cosine goes to 1, so this is very much not, it doesn't blow up. It doesn't go to infinity or minus infinity or anything like that. So this part is all right. Now doing the same analysis, but for cosine of kr over r, we can see that if we do this, the cosine goes to 1, but r goes to 0. So we get 1 over 0, this blows up. It goes to infinity. So that is of course not good, because if we want the wave function to be normalizable, it can't go to infinity, otherwise it just doesn't represent a real physical state. So that means that b needs to be equal to 0. Right? We need that. Or maybe let's do it like this, where we need to impose that. So that means goodbye to this part. Okay, so that is one of the conditions. Now we go for the other. So the other condition was that r evaluated at a needed to be 0. So in that case, we just plug it in here. We get that a sine of ka over a has to be equal to 0. And for this to be 0, we need ka to be equal to n pi, right? With n, of course, being, well, depends where you want to start counting. We can start at 1, because at 0, we don't really have anything. We can start at 1, 2, 3, 4, etc. It depends where you decide to start counting, but it has to be just a whole numbers, right? Entire numbers. So from this, we can see that k is n pi over a. So no surprises, we are going to get, or actually maybe a little bit of surprise, depends. But keep in mind that k, which comes all the way from here, right? That is the k that we are used to. So that we had defined it to be k is the square root of 2me divided by h bar. So if we use that, we get that from here, this is square root 2me over h bar. So we can find the allowed energies. So the allowed energies are going to be E. We have to square this. So we get n squared pi squared h bar squared divided by 2ma squared. And just take a look at this. It is non-degenerate, and it is actually exactly the same that we had in the other cases, right? In the just regular infinite square well. So we get exactly the same for the case L equals 0 that we had for the infinite square well, which is, relatively interesting. Now, what about the wave functions? Well, let's go back here to our expression. So we have r, which is a sine of kr over r, right? So that part we know. So the entirety of the wave function is going to be not only the radial part, but also what depends on theta and phi. So what exactly is this? We have separated, as before, right, into a radial part, which we already found, and the spherical harmonics. In this case, L is equal to 0 and M is equal to 0. So what is that spherical harmonic? We have done videos about it as well. I will put them in the description too, in case you don't know where it comes from. This is simply 1 over the square root of 4 pi. So now what is R? R is, as we just saw, R is going to be sine of kr over r times a. Okay, so we have not yet normalized this. So that is one thing that we still need to go. So the easiest way to normalize this is notice, of course, that a comes all the way from our solution of u. So what we could normalize is simply this expression right here, right? We can normalize u. And since we know that b is equal to 0, normalizing u means normalizing this expression right here, which we have already done because this is exactly the same expression that we had in the case for the infinite square well. So a is going to be exactly the same normalization constant as in the infinite square well, which is square root of 2 over a. So that means square root of 2 over a. And then we can simplify a little bit here. So this would be the 2 cancels out. So we get 1 over the square root of 2 pi a. And sine of kr, but okay, what is k? We can, of course, write what k is. So maybe I'm going to write it a little bit further up. So sine of, now k we said is n pi over a times r. So here we go. This is the wave function in the case of just L equals 0. So you can see that this is pretty straightforward, and this is of course the easiest case, right? Because now if we want to go to, well, when L is not 0, things are going to quickly get a lot less pretty. Now, for the general case where L is not 0, we need to solve this differential equation, and that is not easy. This is actually a special form of the Bessel differential equation, and I made an entire video dedicated to solving this equation. Now, honestly, if you are just taking the quantum mechanics course, solving this is probably way beyond what you need to be able to do. So if you are interested, then I will put, again, a link in the description showing you how this can be solved. I already have that video in my mathematical physics playlist. But if you don't want to go there, it's not necessary. What you need to know is that the solutions are comprised of 2 very special functions, which are the spherical Bessel and the spherical Neumann functions. So the solutions here are just some constant a times r times, and here it is, the spherical Bessel function evaluated at k times r. And then we get some other constant times r times the spherical Neumann function evaluated at kr. Now, what do those functions look like? Well, there is an entire domain of mathematical physics and mathematics in general that just dedicates themselves to studying them, finding their properties. So in the video that I have in the description, I show you how to get to those results. Then the properties, usually you can just find them because they are very well documented, very well studied. So the generalizing functions, you can find them like this. So for example, if you want to find any spherical Neumann function, or sorry, spherical Bessel, let's begin with that, This is for x. Okay, so keep that in mind. This is, now, I don't know this by memory. I'm just copying this from my notes. This is minus x to the L, 1 over x, dx to the L, right? You apply L times this operator to sine of x over x. So that is how you find the spherical Bessel functions. And now the spherical Neumann functions, these are defined quite similarly. It is minus x to the L, and then you have 1 over x, the same operator here to the L, and now you have cosine of x divided by x. So that is how you define those. So we're going to go into them in another video, because we will have entire videos dedicated to knowing how to operate them. But just to show you, a little bit what they look like. So if you plug in j equals 0, for example, of x, you can find this to be, well, quite easily just sine of x over x, right? All of that is power to the power 0. And n0 similarly is simply minus cosine x over x. If you plug in L equals 1, L equals 1, so J1, here you would simply get sine of x squared minus cosine x over x. So you can see that these expressions are very much not trivial at all. And the Neumann function for L equals 1, this would be minus cosine of x over x squared minus sine of x over x. So you can see that you can find any of them, but so what we need to make sure is that both of these functions are actually well defined at 0, right? When r or x are 0. Because otherwise we are going to have something where it blows up, just like in the case L equals 0, and we don't want that. Otherwise we are not going to be able to normalize the wave function. And keep in mind, this is part of the wave function, right? This is part of this u function right there. So what happens as x is very, very, very small? So that means that sine of x is going to be approximately x. And well, you could go to high orders like x cubed over 3 factorial and just continue with the x to the 5th. But of course, if x is very small, then this is not really going to be particularly relevant. But let's see just in case, right? So then we have cosine of x, and that is going to be 1 minus x squared over 2 factorial, which is 2, plus x to the 4th over 4 factorial, and so on. So let's see what happens to these expressions. So in this case, what we get, well, if sine of x is approximately x, then we can go to see that this is going to be approximately 1, right? You're going to have these additional terms which will be very, very, very small, but approximately it's going to be 1. Then j1 of x, you're going to get x over x squared minus, now cosine x is going to be 1 over x. So here we see, of course, that if we don't use higher orders, then we run into some trouble, right? We say, oh, it just goes to 0, but unfortunately that's not quite the full picture. So let's here plug in the second order here. So sine of x would be x minus x cubed over 3 factorial divided by x squared. And then we have cosine, which we could write as 1 minus x squared over 2 factorial divided by x. There we go. So in this case, let's see, this thing would be x over x squared. This thing is simply 1 over x, of course, like before. And this thing right there would be minus x squared. Actually, we were over x squared, so that means that this would be simply x. Minus x over 3 factorial. There we go. And then we have minus 1 over x, which is simply, well, minus 1 over x. Let's just separate this. Minus 1 over x, and then plus x over 2. So this is what we would get. And of course, 3 factorial is simply 6. The 1 over x minus 1 over x, they cancel out. 2 factorial is 2, so we need to find minimum common denominator between those two, which is going to be 6, of course. So plus 3x over 6. So we just add them together. So we get 2x over 6. So 2x over 6. So this goes to approximately x over 3 if we take into account second order. The other ones would be even smaller. The point is that both of these do not go to, they don't blow up, so they are going to be finite. That is what matters. So let's just write it there. So both of these are finite, and in fact, if you keep going, you will see that everything is going to be finite. There's going to be no issues. So the spherical Bessel functions, they are okay. Now, what about the Neumann ones? What about Neumann? Well, if we take a look at the Neumann ones, n0, what do we have? We have minus cosine x over x. So let's approximate it. Minus cosine, we can approximate, well, cosine, we know, is going to be 1, and then we have over x. You could add some other terms, right? You could add the next one, so you get plus maybe x squared over x if you want, and times 2 factorial. But the issue is here. Now we have something of 1 over x, which we did not have before. So this part blows up. And if we go to n1, the next one, so this will be minus, instead of cosine, we have 1 minus x squared over 2 factorial, and we divide each one of these by x squared. And then we have minus sine of x, which would be x minus x cubed over 3 factorial, and we divide all of this by x. So divided by x, divided by x. And I believe that that is correct. I hope so. Yes. So if we continue with this, we see that, well, we have an overall minus sign, and then we have 1 over x squared minus, and here we have 1 over 2 factorial. Then we have plus 1 minus x squared over 3 factorial. So you could simplify some things, but what matters is this. We still have something that is like 1 over x. And the thing is that you will always have it. Every single time, every single spherical Bessel function will have something that blows up at the origin. So for that reason, yeah, we simply cannot use this. So we need b to be 0. So just like before, we need b to be equal to 0. So our solution in the end is simply going to be, well, maybe let's begin with this, like u of r is going to be a r times the spherical Bessel functions evaluated at kr. And if now we want to go for r, which as we saw is u of r over r, well, we simply divide by r and we get a times the spherical Bessel function. So this is our solution, of course. And well, now we want this to be equal to 0 at a. That's our boundary condition, right? Boundary condition means that we want r evaluated at a to be equal to 0. So that means that a times the spherical Bessel function evaluated at a, small a, or rather ka, sorry, so evaluated at ka because r is a, this has to be equal to 0. Now, for this to be true, we need that the spherical Bessel function has to be 0. Unfortunately, the spherical Bessel function doesn't have nice, beautiful, these nice, beautiful expressions where it is 0, like sine, right? In sine, you say, oh, it's simply n pi. It doesn't exist here, right? The spherical Bessel function does not have it. So what we can do is say, let beta of nl, because it depends on n and l, be the number or the value where the function goes to 0. We don't know what it is. You can calculate it explicitly if you know n and l, but there is no overall general way of writing it as we had in the other case, right? So let's just write this as ka. So for that reason, what we can do is say that k is going to be the other way around, beta nl over a. So we can now just plug this back into our solution here and see that the radial wave function is going to be the normalization constant. That, of course, will depend on L, right? You can't just normalize this overall. You will have to normalize it once you know the specific value. you evaluate this at no longer kr, but rather beta NL R over A. So that is the radial part. And of course, well, the actual wave function, this depends on L, L, and M, and R, theta, phi are the variables there. This would be our radial part times the spherical harmonic, which here would depend on L and M, of course, right? And theta, phi. So unfortunately, we can't really find this one general formula, but this is the way to go about it, right? You just plug in your values here, and then you will find your solution for the spherical well, which is actually not that difficult, right? If you know your value of L, you just go to this one, right? You just go here, you just plug in L. Well, you have to take some derivatives, which is going to be a little bit annoying, but that's it. You calculate the spherical Bessel function, you plug it in, and then you can normalize it and find the energies and everything from there, right? You would again have to use the fact that K is related to the energy by this expression right there, and you could find the energy. So that is the way to work with this, and we will very, 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 very shortly begin So we can write this out explicitly, I guess, if we really want to do that. So we could write this as A and L, right? It will depend on both of those numbers, times JL of, actually I need more room, so I will just clear everything. So this would be our constant A. You don't need to write NL, but it is good because that way you just remind yourself that that is what it depends on, right? Times the spherical Bessel function of, and you have to evaluate it at beta and L R over A, and then you multiply this by the spherical harmonic of Lm, which depends on theta and phi. And now, what about the energies? Well, we know that K is related to this beta, and K is also, right up here, related to the energy. So if we know that K is this, but K is also the square root of 2me divided by h bar, then we can see, squaring this and solving for E, that E is going to be h bar squared times beta NL squared divided by 2ma squared. Right, so this is something we can find from that expression. And now, there we go. We have the explicit solutions for the wave function and also for the energy of the infinite spherical well. So what we will have to notice, of course, is that now, since the energy will depend on N and L, so maybe let's write it there, we need to keep in mind that the energy will be degenerate, right? It will have a 2L plus 1 degeneracy. Now, why is that? Well, because simply we have 2L plus 1 possible values for M. Whenever, right, if L is equal to 2, for example, M can be minus 2, minus 1, 0, plus 1, and plus 2. So that all of those different states will have the same energy because the energy doesn't depend on M, right? And that's also why in the case L equals 0, we had just one-fold degeneracy, which means no degeneracy. Okay, so that is the most important thing. And in the next few videos, we will just dedicate ourselves to studying this a little bit more, doing some more examples, and just making sure that we master both, or maybe not master, but get more acquainted with the spherical Bessel functions and also, well, the Neumann ones as well, and also the infinite spherical well, actually in a finite case. So yeah, I hope that this video was useful to you. If it was, please make sure to leave a like on the video, comment, and subscribe, and maybe even consider checking out my Patreon. So I'll see you in another video. Thank you very much for watching.